Hey chemistry students, this is Unit 9 and Lesson 9.1. We're going to introduce you to my favorite chemistry board, stoichiometry. So our goals for this lesson are to first of all explain what we mean by the term stoichiometry, and then to show you how to interpret molar ratios from balanced chemical equations and to solve mole-to-mole stoichiometry problems. Let's get to it.
Alright, so what is stoichiometry exactly? Well, there are Greek origins to the word. The word
Stoichion, I don't know how you say that.
Means element, and metron would be to measure. So you are measuring the elements, so to speak, or the number of elements. So the strict definition of this is stoichiometry is performing calculations that involve quantitative relationships between reactants and products in a balanced chemical equation.
So quantitative means we can put numbers on things, and we can use the number of one thing to predict the amount of something else. So here's examples of the things we're going to teach you to do with stoichiometry. If we give you a certain amount of reactant, so many grams of this or that, you can use stoichiometry to predict how many grams of product or how many moles of product.
And of course, also, if you're given a desired amount of product, you can calculate the amounts of reactants needed. Now, we've been doing lesser forms of stoichiometry all year. We've just been calling it conversions up to this point. But conversions and stoichiometry are related. If you need to pause us to copy down the rest of the slide, pause. Otherwise, we're moving on.
So the heart of stoichiometry is being able to look at a balanced chemical equation and interpret it. So we've written down a chemical equation here. This would be
butane.
Butane, and what kind of reaction, Mr. Hunter?
Well, this would be a combustion reaction because we're burning butane in the presence of oxygen to form CO2 and water.
Okay.
Like we said, 98% of combustion reactions are like this. There are the metal combustions as well. But this on a particle level interpretation, what does this reaction mean to us on a particle level?
Well, I would say that means that there's two molecules of butane, and then they're going to react with 13 molecules of oxygen, O2 gas, in the combustion reaction, and then we're going to get 8 molecules of CO2 and 10 molecules of water. So we can interpret it as molecules. And a molecule of butane would be 4 carbon atoms hooked up with 10 hydrogen atoms, but we can also scale that up. These coefficients are relative amounts that apply to any measure of amount, so we can interpret that most often. We can do it as dozens. 2 dozen of these react with 13 dozen of these to produce 8 dozen and 10 dozen. Of course, a dozen is still not a real useful quantity in chemistry.
Which is why we use the mole. So 2
we're
moles.
Scale it up to moles.
So 2 moles of butane plus 13 moles of oxygen will form 8 moles of carbon dioxide and 10 moles of water.
So when we start talking about moles of things, then we have an amount we can actually work with and realistically measure in a high school chemistry lab. So that's the interpretation. So remember, whatever applies at the particle level scales up to any larger amount, and the mole is the amount of choice.
And we will talk about both of these on our questions, giving both how many particles of this or how many moles of this. So just be ready to see both forms given to you. But let's give you some actual number interpretations of this.
Okay, let's move on.
All right, so here's an actual problem. We have molar ratios, aka mole ratios, are quantitative relationships between components of a chemical process. The ratio is determined by the coefficients and subscripts of the balanced equation. So we gave you an equation of phosphorus with oxygen reacting to form diphosphorus pentoxide. So first of all, we can see how many moles there are between each. So between the moles of phosphorus and oxygen, the ratio would be a 4 to 5 because there are 4 phosphoruses for every 5 O2s. We can do the same for phosphorus to diphosphorus pentoxide.
So we're going to look at the coefficient on phosphorus. We're going to look at the coefficient on diphosphorus pentoxide.
Yeah, so it's 4 to 2. 4 phosphoruses for every 2 diphosphorus pentoxide. And then oxygen to the other would be 5 to 2.
Oxygen to P2O5, 5 to 2.
Those come from the coefficients.
So now, it's not much of a stretch mathematically to say, well, okay, so if you start with 4 moles of phosphorus, that equates to needing to react with 5 moles of oxygen. Or if we start with 4 moles of phosphorus in this one, that equates to production of 2 moles of this. So what we do, we're going to replace the ratio sign with an equal sign.
Yes.
So in other words, the 4 to 5 P to O2 ratio here can be rewritten as 4 moles P equals 5 moles O2. And as long as we are within this chemical process up here of this equation, that's a true relationship.
Yep, and we can use that to convert between the two, just like we've been doing all year between grams and particles and liters and whatever else.
So it starts with an equivalence, and we build the conversion factors from it, and that's the only really new thing we're adding in this unit that you haven't already done.
Even then, it's not all that new yet.
But it's not all that new. So we're just going to say, okay, equate the amounts of the molar ratios. Well, let's show you. Next slide, we'll get to it.
So here's another same reaction, sorry. Start with a balanced chemical equation. You're going to have to be able to do balanced chemical equations as well as take them from words to the actual chemical equation, but in this case, to save time, we're giving these to you. So first off, they want you to calculate from 4 moles of phosphorus how many moles of O2 we should be able to get. So simply, we're going to set up a conversion factor, either fence post or otherwise. And we know that on the bottom we have to have moles of phosphorus. So that means we're going to put the 4 down there.
So the 4 goes here.
And we're going to oxygen.
The 5 goes here.
So it's 4 times 5. Actually, it's just going to be
the 4s are going to divide out, so that's going to work out to 5 moles O2.
There you go.
So that's pretty easy. We're working with the numbers that are already there. But what if we had a different number of moles of phosphorus? So like the second one, now we have 18 moles of phosphorus, but we want to know how many moles of O2 are needed to react with that. Well, that is the very same setup. It's 5 moles O2 to 4 moles P.
And that equates out to be 22.5.
So with sig figs, we're going to write 23. 23 moles of O2. So again, it's we're multiplying the given amount times the mole ratio of 5/4.
Mm-hmm.
All right, now what if we have a smaller amount, like less than 4 moles? We have 0.23 moles phosphorus. How much oxygen is going to react with that? Again, it's 4 moles P to 5 moles O2.
And this comes out to be 0.29.
0.29 moles of O2.
So now let's say we're starting with a different reactant or a different starting point. Now we're starting with oxygen. Now we have 6 moles of oxygen. And
6 moles of oxygen.
Moles of P2O5. So again, 6 moles. We have to set up our conversion factor with moles of O2 on the bottom.
And we didn't show that in the top, but that's so that unit
cancels.
you want to move away from divides itself out.
And also so the particle divides out as well. So we're going to mole of P2O5. And the number for that is 2. And of course for O it is 5, coming from the chemical equation. So it's 6 divided by 5 times 2 gives us 2.4, which just goes to 2 using sig figs. All right, last one. Now we have the reactant, 7.4 moles of P2O5. Again, have to set up our conversion.
And the question's asking us how many moles of phosphorus do you need to make that much?
To get there, yeah. In any kind of chemical process, be it industrial or at the high school level, if you're trying to get to a certain end point, you have to be able to calculate backwards to the starting point. So here we go again. It'll be 2 moles of P2O5 at the bottom.
2, and then it's, what do we want, phosphorus? 4 goes on the top. So the moles of P2O5 divide away.
Divided by 2 times 4 is 14.8, which becomes 15 moles of phosphorus with sig figs. And that's how we do these calculations. They're pretty straightforward.
That's a mole-to-mole conversion rate there.
They'll get more difficult with the next lesson, but in the meantime, we're sticking with these. All right, so here's our next example problem. These are some word problems that you're going to have to deal with. First, it's how many moles of carbon dioxide are given off when 3.4 moles of butane are completely combusted. So first of all, we have to know what a combustion reaction is, so we know what the other reactant is with butane.
So I know in the combustion it's going to be something plus O2, and we're always going to get some CO2s and some H2Os. So we need to figure out what butane's formula is, and we need to balance it. Butane,
F-prop-bute, so it's C4.
C4.
Again, H10.
H10.
All right, so to balance this, we need 4 CO2s. We need 5 H2Os. Yeah, 5 H2Os.
5. Uh-oh. That's going to give us an
It's
odd
okay.
number of oxygen.
We'll deal with it. 5 H2Os. So that doesn't give us. It gives us 8 plus 5, which 13. So we need 6.5 O2s. Yeah, 6.5 O2.
6.5. Or we could double everything if you want to get rid of the fraction.
But we'll leave the fraction for now for simplicity's sake. Granted, we're not supposed to do that, but with any diatomic, you can write it as a half to balance things out.
Sometimes see them that way, even though we tell you you're not supposed to.
Professionals do write it this way. I've seen it in ExxonMobil written that way, so it's not the end of the world.
So let's kind of look at where we're at. We know we have 3.4 moles
of butane. So C4H8.
C4H10, right?
Yeah, H10 was butene.
Okay.
So now we have to figure out our ratio between butane and
we want to know how many moles of CO2.
So we know it's for every 1 mole. All right, I'll let you write your little thing down there.
And the only thing that does get annoying is you have to keep writing the substance, but that's really important now because we're switching between substances, so you need to keep that straight.
So our conversion factor between these two is 1 mole because the subscript up, or the coefficient up there for butane is 1. And we're going to CO2, and that one's coefficient is 4. So it's CO2. That gives us CO2 at the end, so it's going to be 3.4 times 4 to end up with 14 with correct sig figs moles of CO2.
So again, it's applying the dimensional analysis or the fence post. Cancel the unit you don't want, get it to the unit you do want, and this time the equivalence comes from the balanced chemical equation.
All right, so the same equation above, we want to know how many moles of butane are needed to produce 0.43 moles of water. So what we need is 0.43 moles of H2O. Plug in our conversion factor.
So again, we know we want moles water down here, and we want to go to moles. That's moles of butane, C4H10 up there. So go up to the equation, pick it out. Water has a 5. Butane, 1.
So it's going to be 0.43 divided by 5. You need 0.086 moles of butane. And that's how these are done. Let's try one last practice problem.
So here's a final example. This is a neutralization reaction. How many moles of sulfuric acid are going to be required to neutralize 0.19 moles of sodium hydroxide? So we've already written the equation out and balanced it. So the ratio is 1 here, 2, 1, 2. And we know we have 0.19 moles of this. We're trying to figure out how many moles of that.
To exactly react, yeah. So here we go with our...
So how many moles of H2SO4 do we need to neutralize 0.19 moles of NaOH, sodium hydroxide?
Of course, we need to set up our equivalents. So we know at the bottom we need moles of NaOH, and that's going to be 2 moles of NaOH on the bottom, coming from the chemical equation.
That's that number right there.
And then at the top, we need moles of H2SO4,
Whoop.
which we know to be 1 mole of H2SO4, again, coming from the chemical equation.
There's no number written there, so we know it's a 1.
So then when we do the math, we have 0.19 divided by 2, and that equals 0.095. And that's how we neutralize that much sodium hydroxide. That's not
That's
NaOH.
H2SO4.
All right.
All right, we'll give lots more practice in class, but that's the basics of mole-to-mole stoichiometry conversions.
All right, have a good night.
All right, chemistry students, so here's the post-video questions for lesson 9.1. So we need you to balance the equation shown below, and then answer the 3 questions. Get that done so we can discuss it the next time we meet in class. Until then, I'll see you.